Welcome everyone. My name is Marnix Wagemaker and I'm an Associate Professor in Battery Technology at the Delft University of Technology. In this lecture, I will give an introduction to EV batteries. Batteries can store energy and are used to power a large variety of devices, ranging from micro batteries that maintain the memory of computer chips up to big batteries that power electrical cars and stabilize the electricity grid. Batteries that can only discharge once are called primary cells. For example, our well-known AAA and AA alkaline batteries. Batteries that can be recharged are called secondary batteries, examples of which are lead acid, nickel metal hydride and lithium-ion batteries. Batteries consist of a positive and a negative pole, or electrode. In a charged battery, energy is stored in a chemical form in the electrodes, which is released as electrical energy when discharged. Vice versa, secondary batteries can be charged using the electricity, which is electrical energy converted to chemical energy stored in the battery. An important characteristic of batteries is that the energy storage efficiency is very high, mostly more than 90% in lithium-ion batteries. In an electrical vehicle, all the energy needed to drive is stored in the EV batteries. Moving from fossil fuel-powered cars towards battery-powered cars is challenging. First of all, because fossil fuels, such as diesel and gasoline, have a large gravimetric energy density compared to batteries. Because a car needs to be as light as possible, the battery cannot be too heavy. And this limits the maximum amount of energy stored in an EV battery, which itself limits the driving range. Lithium-ion batteries currently have the highest gravimetric energy density of all battery technologies. Therefore, they are widely applied in electrical mobility today. State-of-the-art lithium-ion batteries have an energy density close to 250 watt-hours per kilogram, which is still relatively small compared to the energy density of fossil fuels. Gasoline, for instance, has an energy density of 12,900 watt-hours per kilogram. However, an electric engine is roughly 4 times as efficient as an internal combustion engine in converting chemical energy into mechanical energy. Thus, an EV battery needs to be roughly 13 times as heavy as a gasoline tank to reach the same energy content. We should distinguish gravimetric energy density from volumetric energy density. Suppose a 70 kilowatt-hour battery is demanded in an EV. This results roughly in a battery of 300 kilograms, taking a volume of approximately 100 liters. This is quite a limited volume, hence the weight is typically the limiting factor for EV technology. Another demand for EV batteries is fast charging, as this determines the time someone needs to spend to recharge an electrical car. How fast the battery can be charged or discharged is quantified by the power density, which combined with the energy density is visualized in what they call a Raguni plot. Given the demanded energy and power requirement for an EV battery, we can determine if power density or the energy density determines the weight of the battery. Suppose a battery energy of 70 kilowatt hours demanded with a required maximum power output of 50 kilowatt. What would be the weight of the battery? This is what we can determine from the Raguni plot. Also, cycle life, which is the amount of cycles a battery can be recharged, is an important characteristic, as this determines the total lifetime of the battery. The cycle life depends on the operation conditions, including the temperature, the charge rate and the load profile. Safety is a major concern for EV cars, and the safety specifications depend on the chemistry of the battery and its use, for instance, including the C-rate. In an EV, many individual cells are combined into a battery pack. For example, a Tesla car with 85 kilowatt-hour battery pack contains 7,104 individual cells. A crucial component of a battery pack is the battery management system, which monitors the state of the individual cells and manages how the individual cells are charged and discharged. This is vital to achieve safe operation, a long cycle life, and optimal performance. The two most common lithium-ion battery shapes are cylindrical and prismatic cells. Typically, cylindrical lithium-ion cells are used in EV technology as they provide the longest cycle life, a high safety standard, and they are cheaper to produce. The disadvantage is that they are less efficient in volume packing of multiple cells, simply because of their shape. However, for cooling the cells, this is actually an advantage. Prismatic cells are more volume efficient, and for this reason they are typically employed in mobile phones and tablets. The total cost of a battery depends on the battery materials and the battery production. The cost distribution depends on the specific battery chemistry and the different components. Lithium-ion batteries have become cheaper per watt-hour energy storage because of scaling up production, increased energy density and cost reductions. For instance, by reducing the amount of cobalt in the positive electrode. Recycling will become increasingly important in the future to recover the elements and materials from lithium-ion batteries, as increasing production volumes of batteries will put pressure on the price of battery materials as well as on material availability. As I explained before, electrical cars require batteries with a high energy density to provide a large driving range. In addition, a long cycle life is important to guarantee a large total driving distance before the battery needs to be replaced. Current lithium-ion technology has safety concerns which are related to the liquid electrolytes in these batteries. The battery performance as well as its safety is determined by the electrode and electrolyte materials. Therefore, worldwide battery research aims at finding new materials and battery chemistries that improve performance, safety and cost parameters. Current lithium-ion batteries are close to the maximum theoretical energy density, which is anticipated to be around 280 watt-hours per kilogram. New lithium chemistries are being developed to cross this limit. These new chemistries include, for instance, lithium sulfur and lithium air. At the moment, these chemistries have many challenges, in particular their cycle life, which is related to the large structural changes and reactivity with the electrolyte. With respect to safety, research is focusing on the development of all solid-state batteries, where the liquid electrolyte is replaced by solid electrolyte. Lithium is relatively abundant, but geographically mainly found in a few areas around the world. Also, lithium is present in the oceans, but efficient lithium extraction out of seawater is not cost-effective yet. Therefore, other charge-carrying ions are considered in research for EV batteries. For instance, the multivalent magnesium ion. That is an interesting alternative as it carries 2 electrons per magnesium ion. Challenges of this chemistry, for instance, include the reactivity with the electrolyte. Intensive research is necessary to see which chemistry will be able to cross the energy density limit of lithium-ion batteries. And this ends our introduction in EV batteries. Thank you for watching and see you in the next lecture.